high, we continue to discuss two-sample t-tests. So now that we think about the case that the sigma x is not necessarily equal to sigma y. This is more realistic case. But the drawback is that there is no beautiful theory for testing mu x is equal to mu y under. Okay, so but still that we have some approximate result. So if sigma x is not equal to sigma y, we define the t statistic as x bar minus y bar. So this is the primary quantity, and divided by square root of s sub x square over n plus s sub y square over m. So this is actually just the derived by the same philosophy as the last time. So x bar follows normal, the mu x and sigma x square over n, and y bar follows normal, mu y m sigma y square. So if we think about x bar minus y bar, that is normal mu x minus mu y, and the variance sigma x square over n plus sigma y square over m. So just we put square root of this to get the t statistic. And here the degrees of freedom k. So last time that we have n plus m minus 2, okay? But now that we have slightly different value. And actually, formula is very complicated. So k is given by this quantity. So this is not necessarily integer. But k is usually the between n plus m minus 2 and I would say the minimum of n minus 1 and m minus 1. The idea is that if s sub x and s sub y are the same, if these numbers are the same, then we will get somewhere, we will actually get n plus m minus 2. But suppose that the sum, the one number is larger than the other. For example, sx is much larger than sy. Okay, for example, 10 times larger. Then basically the second term, the smaller one, does not really matter for the statistic. Okay, so in such a case, this degrees of freedom approaches to n minus 1 because s sub y square doesn't have any, much variability. So then n minus 1. So if the one s sub x square is much larger, then k approaches to n minus 1. If s sub y is much larger than s sub x, then degrees of freedom approaches to m minus 1. So k is somewhere in between. So that is the idea. And so the exact formula is here. And this is called and the rejection region is given in the same way. And this is called the Welch's t-test. And k may be fractional, such as, okay, so 10.5 or 11.9. So, so for this, the specific example for the Detroit and the Dearborn case, the n plus m minus 2 is 10. So not more than 10, but maybe 8.8 or 7.5 is the degrees of freedom. And here, you wonder what's the t distribution with df 7.5? So originally, t distribution with degrees of freedom, k, is defined by the distribution of the z naught divided by square root of summation of z1 square to zk square and divided by k, then square root. So this can be defined for only positive integer k. So k is equal to 7.5 does not make any sense. But actually you can define this because this distribution, the probability density function has this form. So this is pretty complicated form, but basically 1 plus x squared plus over k to the power the negative k plus 1 over 2. And this is the first part. The first factor is the normalizing constant. And you can extend this definition for any k. Actually, maybe larger or equal to 1. K is larger than or equal to 1. But you can define this for any k. So actually, t distribution is defined for fractional case. Yeah, so this is example. So t dot test. Last time that we used the t dot test, the dt db, and we put the variance dot equal is equal to true. But if we don't put that, then the R can implement the Welch's t-test. And the t-statistic, the negative 2.24, and degrees of freedom is 9.917. Actually, this is similar to the previous one. So last time the DF was 10, right? So 7 plus 5 minus 2, so 10. So it's really close. So both sample have almost the same variance. So that's why DF is almost the same. And p-value is slightly different, and actually it is below 0.05. So it's really hard to say that we should reject or not. Anyway, 0.05 is also somewhat subjective threshold. So in this case, we reject the null hypothesis that mu x is equal to mu y.